There's like some running rule that gives me so you do one thing.
Okay, hi everyone. So this time we have a guest lecture by Sean, and this is based on a survey paper that he led on inference time algorithms for large language models. It's going to be a tutorial at NeurIPS, right?
Mm-hmm.
So you get to see the tutorial here 2 weeks before his actual tutorial at NeurIPS. So please give him any feedback if there was anything that he could improve it for that as well. But ask lots of questions and yeah, please go ahead.
Okay. Yeah, thanks. So today I'm going to talk about inference time algorithms for large language models. Is this too loud or okay? Good. Okay. And at its core, I'm going to be talking about algorithms for generating outputs with a language model. And so why should you be as excited and interested in this as I am? Well, really, right now in the field, a lot of people are thinking about how we can take an existing model and somehow use compute at test time, so after it's been trained, in order to improve the performance of the model. And so the algorithms that I'll tell you about today are ways of doing that. And we'll be talking about language models, which are also themselves pretty exciting, because it seems like every day you can do a wider and wider range of things with them, ranging from solving Olympiad problems to writing code in your code base to essentially anything that you could frame as, generating an output sequence. And when we think about how these models have progressed over the years, you can think of it from the perspective of scale. So the first wave of scale was around scaling the amount of compute that is used to pre-train the model. So this is a really famous result from OpenAI. And on the x-axis, you can see the amount of compute that's used at pre-training. It's related to the size of the model as well as the number of tokens that the model is trained on. And then on the y-axis, you can see that the model's performance in terms of test loss is kind of predictably improving. And so this is really exciting. But since then, people have found that this hasn't really been sufficient so far to do all of the tasks that we want with the language model. So then there was kind of a second shift to looking into what is called post-training. And here's an example from a paper, that you might have seen in the class, where they essentially collect all of these different input-output pairs and then fine-tune the language model on them. And it can do better on the tasks. It can even generalize to some new ones. And so this has led to these extremely flexible and often useful assistants that we have now. But people started realizing that like this also wasn't sufficient, especially for some of the more complex or challenging tasks that we want to do. So recently there's been a third shift, and it's about taking an existing model that has already been trained and then trying to use compute at test time. So throughout the talk, I'll also say inference time or generation time and try to get better performance with the model. So here is a recent model that was released called O1 from OpenAI. And on the x-axis, you can see the amount of compute that it's using at test time. And then on the y-axis, you can see its performance on this pretty challenging mathematical reasoning benchmark increasing. So how is this possible, and what are some different ways for achieving this? Well, we don't actually know the exact recipe for what OpenAI specifically is doing, but there have been a few common patterns that have emerged and are relatively well studied in the field. So one is to say, well, we're using language models, so why don't we spend extra compute at test time by just generating more tokens with them? And when you think about it, kind of each time you do a feed-forward pass with the model, you're in some sense spending some compute. And so maybe if you generate more tokens in a certain way, that could actually improve your performance. So one example of this is called chain of thought. And here we prompt the model to generate these intermediate thought tokens shown in green. And it turns out that this can have a substantial impact on how the model scales as it gets larger. So for example, on the right here with these palm models, it was looking like the model wasn't going to be that promising on even this pretty simple benchmark. But then by doing this chain of thought prompting, the scaling behavior completely changes. Now, it turns out that there's actually several reasons for why the chain of thought works. But for the purposes of this talk, we can view it as, some technique for generating these extra tokens and potentially trying to get better performance. The second thing you can do is to just call one of these generators multiple times. So here's a famous example called AlphaCode. And on the left-hand side here, you can see that their model has undergone these two stages that I told you about, so pre-training and fine-tuning. And then at test time, what they do is not just have the model generate one output program, but generate thousands or even millions of output programs. Then you can filter them and cluster them, and then ultimately just treat a small number of them as the final output of the system. And then this can also have a substantial impact on the performance. So here on the x-axis is the number of samples that are being drawn. And then you can see on the y-axis that the pass rate is really improving for a wide range of model sizes. And then recently we've seen these kinds of curves, performance curves, show up in many different domains. So ranging from math to these coding agents to also just kind of general purpose chatbots. And then the third shift that is kind of happening is thinking about how we can integrate an individual model with other models or external tools. So for example, instead of just using a language model by itself, you can incorporate it with some evaluator model or verifier model. Or let's say you're, solving a math problem. Why don't you actually offload some of the computation to a calculator rather than having your model do it? And so these three different patterns are kind of different ways that you can improve a model after it's trained. And today I'm going to tell you about a kind of common framework for thinking about these called meta-generation algorithms. And then once we have the framework, we can look at some patterns that have come up in, in the literature. So first, let me tell you what a generation algorithm is. And that just refers to any algorithm that takes in some input and your language model and then produces an output sequence. So you can think of this as like calling a language model API. And these are implemented with traditional algorithms like greedy decoding or temperature sampling or beam search. And if you're not familiar with those, I'll go over those as a review in the first part of the talk. Then a meta-generation algorithm is a kind of higher level algorithm. So it'll again take in some input X, but now the algorithm itself will take in these sequence generators. Moreover, it can also take in these external models or functions. So let's say you have an evaluation model, then you could provide it to the meta generator. Finally, a really key parameter will be the budget, or for instance, the amount of tokens that you use to ultimately produce your final output sequence. So a really simple example is, let's say you call your language model API multiple times, and then you have an evaluation model and you select the best sequence. And again, given this framework, you can increase this budget parameter to hopefully improve your task performance. You can combine multiple models and then incorporate external information, such as like tools or feedback. So in this talk, I will first go over how you just generate one sequence with a language model, so these generation algorithms. Then I'll talk about 4 different strategies or patterns for the meta generators that have kind of emerged in the field. And then I'll have a section on how you scale up these meta generators. So how we can think in kind of principled ways about choosing meta generation configurations, and then some techniques for how you make them fast. And as Graham mentioned, this is a part of a tutorial that'll be presented at NeurIPS. It'll actually be 2.5 hours if you want some more content. There'll also be code examples in the tutorial, as well as a panel and Q&A session. So for the first section is on how we generate just a single sequence with a language model. So these language models are autoregressive, and this means that they decompose the probability of a full sequence into these conditional distributions. And each conditional distribution gives us a distribution over the next token. So like here, for example, we have this prefix or prompt about Taylor Swift, and then we pass it to the language model, and it gives us this distribution over next tokens. Then we can choose a token and put it into the prompt, and then repeat the process. So now we get a new next token distribution, and then you can keep doing this until you get a full sequence. So really, these token level generation algorithms or decoding algorithms are really concerned with how what is the strategy you use to choose the next token. So you can view this as a kind of search process through this exponentially large space of possible output sequences. And if you view this as a search, then a natural question is like, what are you searching for? What is the objective of the search? And then once you've defined the objective, how do you actually perform that search? So how do you make these local choices about choosing the next token to ultimately achieve the objective? So ultimately, when you're designing a generation system, one way to kind of formalize the task is to say, okay, I want to design a generation system that gives me some notion of acceptable sequences. So in some cases, acceptability might be really clear, like you're trying to solve a math problem and you want the sequence to be a correct solution. In other cases, it's a lot more difficult and maybe subjective. Like, let's say you deploy a chatbot and you want the human user who's looking at the output to kind of prefer the outputs from your system. Now, if we just look at these kind of low-level algorithms where we just have a language model, then when you think about it, there's really only 2 options. You can try to maximize the probability, so find the output that has the highest probability. Or you can, since it's a probability distribution, draw some sample from the language model. So let's look at the first one. This is traditionally known as map decoding or maximum a posteriori decoding, where we try to find the most probable output from the language model. And the simplest possible thing you can do is to basically at each step, just choose the token that has the highest probability. So here's an example. This is an actual example with a GPT-2 model. And here what we're doing is at each step, just choosing the token that has the highest probability. And so you get this continuation. And the total probability is this number here. Now, it turns out that if at the first step, we would have chose this word singer instead of the word former, then singer itself has a lower probability, but we could have ended up with a sequence that actually has a higher probability. And so the lesson here is that, these local decisions that you're making aren't necessarily globally optimal, right? Like the local decision to choose former ultimately leads to a sequence that is actually lower probability. So to get over this, another method that's used is called beam search. And so here what we do is we consider multiple candidate next tokens at each step. And then in this example, we have a beam of size 2. So we're going to save the top 2 most probable tokens. Then we can expand the beam and then basically repeat the process where we save the 2 highest scoring prefixes so far. And then you can repeat this and kind of roll out the tree and eventually get some full sequences. Now, if you think about it, if you were to just make this beam of size 1, then that would actually be this greedy decoding procedure, where you're just choosing the most probable token. So this beam search is a kind of generalization. Now, beam search is, it's a very popular decoding algorithm, and it was especially widely used in, these like translation systems, as well as systems that did these closed-ended input-output tasks. Things like translation, summarization, question answering. And so what happened is, in the age of language models, people started using language models for more open-ended tasks. Things like generating a story or, just having a conversation. And it turned out that actually with these map decoding methods, there started to be kind of really odd behaviors that people started seeing. So one of them, I'm not sure if you've used one of these language models from a few years ago. One of them that you would frequently see is these odd kind of repetitive loops. So the model would just go into this loop and it kind of had no hope of recovering. And so the really weird thing is, if you think about it, this sequence probably never occurs in the training data. So it's kind of puzzling why this is happening. The other thing is, like on the other extreme, researchers found that sometimes the model would actually assign very high probability to this special token that ends a sequence. And in fact, there's this pretty cool paper from 2019 that actually did an exact search. So it found like the sequence that really did have the highest probability. And it turned out to be the empty sequence for one of these translation models. And there's different ways to think about this. One way that I think is really compelling uses the idea from information theory called typical sets. And so the idea here is, if you can imagine flipping a biased coin 100 times, then it turns out that the most likely outcome, so the kind of highest probability sequence of 100 flips, would actually be to get all heads. Because what you would do is you'd multiply this 0.6 100 times, and if you ever introduce a tails, then it's going to be lower. Now, the thing is that like if you were to actually simulate this this process of doing 100 flips, you would pretty much never get this sequence of 100 heads. And so this idea is referred to as the typical set. So the typical set is the things that you get almost always if you actually sample from the process, but there could be these kind of outlier points that individually have higher probability. And so one way to potentially think about these repetitive sequences, or like the short ones, are these kind of outliers. And unfortunately, in practice, the decoding algorithms can actually find those. So one workaround is to just use a sampling algorithm. And if we look at if we look at like some common language modeling APIs, here's one called Together AI. You can see that they don't actually offer this beam search option. But they offer these different knobs, which I'll tell you about in a second, like temperature, top P, and top K. The repetition penalty is interesting, and we'll actually think about that one in a bit. So for sampling, you again take advantage of the fact that the model is autoregressive, and you basically just sample one token, put it into the prompt, sample the next one, and then continue. And then this turns out to be equivalent to sampling from the full distribution over sequences, since the model is autoregressive. And so not all generative models are like this. With some generative models, it's actually very difficult to sample from them. So this is like yet another nice thing about today's language models. We can actually get these samples, fairly easily. So stepping down one level, how this is actually implemented is you do this feed forward pass with the model, and you get what are called logits, and then you take the softmax. And the reason I wrote out the softmax in this form is because a very frequent thing to do is to actually modify this distribution. So one way to modify it is what is called temperature sampling. So temperature sampling just divides these logits by this parameter, which is called the temperature. So what effect does this have? Well, as you make the temperature lower and lower, it'll make the distribution more and more peaked. And in fact, if you take the temperature to 0, you actually, the distribution will peak over the most likely thing. And so you can actually get this greedy decoding as a special case. So I'm pretty sure that's maybe why these APIs still have the repetition penalty. Because like if you turn the temperature too low, the model might actually start repeating itself. And then you can modify these token distributions in different ways. Two other common ones that you saw on that API are top P and top K. So top K, it's a bit small, but it's basically what it sounds like. So you look at the next token probabilities, you choose this value of K, and then you basically zero out everything else. And so like in this example, if you zero out all these probabilities on the left, then you could see that it prevents the model from, sampling this end of text token. So sometimes these different heuristics can, fix some of the issues you see in certain cases. Top P is another one where you now sum up the probabilities until they exceed this kind of cumulative budget. So that was a quick overview of some methods for just generating one sequence with a model. And so hopefully, if you hadn't seen that before, now you have some understanding of what happens if you're calling, an inference library or a language modeling API. And so now in the next part of the talk, we will treat these as a kind of black box and think about higher level algorithms for generation. And so those will be called these meta generation algorithms. So again, we want to design some system that generates acceptable sequences. So things like correct sequences or ones that have high preferences for users. And what I just told you about is how you can sample outputs that are kind of probable. But then the question is like, what if there's a misalignment? So what if the samples that you get aren't actually acceptable? Well, there's kind of two ideas that you can take advantage of. And these two key ideas kind of underlie the different strategies that I'll tell you about. The first is that you can use information that is outside of the language model. So an example is you can learn an evaluator model. that actually tells you whether things are acceptable or not. And then if you had such a model, well, first, it turns out that these evaluator models go by many different names. They could be called critics, verifiers, value functions, reward models, and scoring models. So I think throughout the talk, I'll use the term reward model. But it's even hard for me to use one word. And so you kind of just have to get used to seeing these different terms. Now, if you had this, you can use a pretty simple strategy, which is to just call your generator more and more, and then eventually find some output that is acceptable according to your evaluator. And so just to make this concrete, you don't have to read through all the math here, but let's just look at a concrete example where we want to generate an output. We want to solve this math problem. So here we have an input X, and the model will generate this solution, which we'll call Z. And then at the end, finally generate some final answer, Y. Now, what would happen if we had an oracle verifier or reward model? So this model would tell us exactly whether this answer was correct or not. Well, then we could design the following strategy. We could repeatedly just generate a solution and generate an answer, and then stop if we ever get an answer that is correct. And then just repeat that procedure forever. It's still not trivial because, given this problem, you don't necessarily know what the answer is. But, certainly you could do this strategy. So it turns out if you do this, then it can actually work, well on a pretty difficult benchmark. This one's called the math benchmark. And so you could see here on the x-axis, the number of generations as it's increasing. The number of problems that you're solving is increasing, in some cases, going up to 100%. Now, I know what you're thinking. We don't always have this Oracle evaluator to, tell us whether the problem is correct or not. And then moreover, the strategy that I wrote down on the previous slide, it's maybe the most obvious thing you could think of. And so possibly there's like more clever ways of calling these generators and incorporating things like the evaluator. And so these kinds of strategies are what we will refer to as meta-generators. You take in some output and then internally call a language model, and then you can take in other parameters like an evaluator model, the number of times you want to generate, etc. And you can view these token level generators as a kind of special case where you're only taking in the language model and your strategies are things like, are you going to sample? Are you going to use beam search?
I wanted to go back to the graph. So by at least one correct, does this mean for the entire math data set that given 10 to the power of 4 generations, there are at least the model is able to correctly answer for all of the samples?
Yeah, so this should be problems solved. So it's saying out of the, so for a given problem, let's say you draw 1,000 samples, is one of those samples at least correct for this problem? And then you average that over all problems.
I see.
So this y-axis is really showing percentage of problems that have been solved.
That makes it even more interesting because that means a model as small as a 2 billion parameter model could actually achieve almost 100% on this data set. Like Gemma 2B, right? The light green one.
Isn't that the llama again? The Gemma is the
This one.
Yeah.
Yeah. I mean, so the Gemma model probably has been trained on the math training set.
Oh,
So it does get tricky to think about some models just in terms of the parameters. But yeah, it is kind of striking to see, if you could perfectly evaluate how big of a difference. Now, in practice, it'll get, it'll be very far from this oracle, but it's just showing the idea. And so, yeah, I'll talk about 4 different strategies. So chaining, parallel generation, tree search, and refinement. So chaining is a kind of intuitive idea where we basically call a generator and then take the output, call another one, and so on. And a motivating example is to think about this chain of thought method that I told you about before as a kind of 2-part decomposition. So first we have the model generate this thought, Z, and then we call the generator to finally generate its final answer. And the reason it's maybe interesting to think about this way is you could think about generalizing it to more than just, two steps. And so an example of this is this method called self-ask. And this, in some sense, generalizes it to multiple steps. So at each step, what they do is they have their model generate some query, and then they actually call this external tool, which is like a search engine API, and then get some answer. And then you can do it again. You could generate another query, get an answer, and then eventually output your final answer to the question. In some sense, you can view this as a program where the meta generator is the kind of outer program. And then your function calls within the program are things like calling the language model to generate, calling this retrieval system or search engine API, and so on. And so if it's helpful, some people find it helpful, or, in some settings, it's helpful to think of these as programs. And in fact, this idea has come up in various forms throughout the literature. One of them is called language model cascade, or, in a few cases, they are just called LLM programs. So you might see those terms come up. And then you could imagine basically building any one of these chains that you think of for your application, ranging from rewriting an input before doing your final generation. Or here's an example chain that we made to generate these formal proofs where you break it down into kind of 3 different steps. And so the key idea is the chain gives you some way of decomposing generation and a really natural way to think about calling some external tool or external model. Now, if you just think about generating one of these chains alone, then it's not really exploring the space of possible outputs. And so that will motivate the next pattern, which is called parallel generation. So parallel generation is, again, idea is very simple. We have some input, and then we call our generator and have it generate n outputs in parallel. Then we pass those outputs to some aggregation function, and then eventually get the final output of our system. And so one of the key questions is like, what aggregation function do you use? And one option is to just take the maximum. So here you have some scoring model or reward model, and it's basically going to assign a score to each one of your outputs. So like here, 2 + 2 = 5 gets a low score, whereas 2 + 2 = 4 gets a high score. And then again, you just take the maximum, and in this case, you would return 2 + 2 = 4. So simple idea, but very effective in practice, and it goes by different names like best of n or rejection sampling. It's kind of interesting to think about, why would you want to do this in terms of the goals that that we were talking about? And what this best of n procedure is doing is actually approximating the search for the most acceptable output. So there's kind of two steps of the approximation. In the first one, we're saying that by drawing just n outputs, we are approximating the maximization over all possible outputs. And this is really cool because as you kind of increase your compute budget or as you generate more, the approximation gets better and better. Then in the second step, you can actually run into issues. It's basically saying that your reward model is some approximation of the notion of acceptability. So for example, in the case of the math problems, if you have a model that detects whether a solution is correct or not, sometimes it'll actually be wrong, and the solution will be, sometimes it'll be wrong. And so in practice, this can lead to a phenomenon that is called over-optimization. So here's an example paper that did do this for math. And so they trained these evaluation models to check whether a solution was correct or not. And then they did best of n. And you can see here that as you scale up the number of generations, initially the solve rate is improving. But then eventually the best of n starts finding these sequences that the evaluator thinks are good, but then are actually kind of like incorrect solutions.
In practice, are these evaluators trained independently of the model according to the domain or together?
Yeah, so that's a great question. So I'll give a couple examples in this talk, but how you train the evaluator is, very important, and there's different strategies you can take. The simplest one, or like the one that they did here, is you take a model, you generate a bunch with it, and then you can actually check whether the answers are correct or not on your training set. And then you just, train a model to take in a solution and then predict whether it's correct or not. So kind of binary classifier. Yeah. So as I mentioned, I'll go into a couple ways where you can improve the scoring function or reward model. But the other thing you can do is to just change the aggregation function that you use. So the other one that's common is called majority voting, also goes by the name of self-consistency. And so here, again, the idea is very intuitive and very simple. Here, we're going to assume that our output ends in some kind of answer. And then we're going to choose the answer that just occurs the most often. So for example, in this case, the answer 2, occurs the most often. So that'll be the output of our meta generator. Now you can actually incorporate your reward model into the voting by first scoring your outputs and then doing a kind of weighted vote. So now every answer is not just going to count for 1, it's going to count for the score that your reward model gives it. So like in this example, it is able to kind of break this tie between the answer 2 or the answer 4. Okay. And so it turns out that this weighted voting procedure can actually do a lot better. So here's an example of, increasing the number of generations. This is again on this math benchmark. And you can see that this gap opens up between best of n, majority voting, and this weighted voting procedure that I just told you about. So how do we think about, a bit more carefully about what this voting procedure is doing and why you might want to use the weighted voting one specifically? Well, we can actually, develop a bit of theory about this weighted voting. And there's this kind of cool result you can show. And it basically says if you were to scale up the number of samples to infinity, what would the accuracy with weighted voting converge to? And it ends up converging to this thing shown here. And what it's saying is it's the accuracy you get if you were to sum over or marginalize over all possible intermediate paths. And so it's kind of a nice intuition. It's saying that like, okay, the voting procedure is taking into account all possible paths to the answer that your model kind of knows about. And then you can also see here that this your reward model ends up showing up. So it can have a kind of impact on the results. So you can get at least three takeaways from this. One is, if I was to just keep running weighted voting with more and more samples, would I kind of solve everything? And in most cases, the answer is going to be no, because you'll eventually just converge to this thing shown here, the accuracy shown here. You can also think about when is weighted voting better than voting. And it's when your weight times your generator probability is assigning more total mass to correct answers than just your generator alone. So again, this is a kind of intuitive idea that if your reward model is kind of slightly better on average than your generator at scoring correct answers, then you're going to do better with the weighted voting. And then finally, how can we possibly improve performance further? If we're going to converge to this accuracy, well, you can still improve the reward model, and or you could improve the generator. So you could either have a better language model or even develop a better generation algorithm for getting your candidates. So improving the reward model is, itself a very active area of research. Here's just one example. It's called generative reward model. And the reason I'm showing it is because it's actually using the idea that I just showed you, but to actually implement your reward model. So they actually sample multiple chains of thought and then say, is this solution correct or not? And then you can take the average. So in summary, these parallel meta generators will do some exploration of the output space by generating full sequences. And in practice, this can lead to pretty large performance gains. However, they're ultimately bounded by the quality of your evaluator or reward model and your generator. So one insight is that these algorithms are kind of only using this verifier or reward model at the very end, once you've generated a full sequence. And so the question is like, can you do a bit better if you somehow leverage evaluation on intermediate parts of your generation? Mm-hmm.
Yeah, the question. So here we are evaluating sequences when they are fully generated, right? Versus something like beam search, we are doing it at system level. So there's a trade-off in terms of the cost. Like how would you compare it?
Yeah, so that actually leads, so the next thing is about tree search. And so here, instead of doing the tree search at the level of individual tokens, now we'll do it at the level of like, one step of a solution, which itself can be multiple tokens. And then in fact, we'll answer your exact question, which is like, how can you compare these on an equal computational budget basis? So tree search, like it sounds, is you form this kind of tree. And the idea is now you decompose your generation process into a sequence of states and different transitions. So like in the case of solving the math problem, one of your nodes or one of your states might be one step of the solution. And then, the next state would be generating the second step and so on. Then you have to come up with some score of each one of these nodes, and then run a tree search algorithm like breadth first search or depth first search or beam search. And so again, your design choices, for your application are, can you come up with a kind of meaningful state space? And then what are these different transitions? This shouldn't have this should be S. And then finally, how do you come up with these scores for the intermediate states? And then what tree search strategy do you actually use? So let's look at a concrete example. Again, using the math problems, and then I'll show you some other examples from other domains at the end. So here, what is done is you learn what's called a process-based reward model. So the process-based reward model will take in just the steps that you have so far in your solution. And then it'll try to predict the, either whether there's an error in the current step or whether the solution will eventually be correct. So if you're just trying to predict whether the current step is incorrect, you can actually have humans, go through and annotate this. And that's actually what OpenAI did. They got all of these human annotations for different steps of math problems. Or if you want a more automated procedure, you can take a model and then kind of keep generating with it, and take the average of at the end, and that gives you some expected expected correctness or expected reward. So now you have some way of assigning scores to different nodes. Again, a node is just going to be a step as well as the preceding ones. And then the question is like, what is an example tree search algorithm that you can actually use? So here's an example one called Rebase. And this one is kind of designed to use this process-based reward to control the exploration of the tree search. And so the idea is pretty intuitive. It's basically you look at your current frontier of nodes that you have, and then you have to decide, which ones am I going to explore next? And it basically chooses how much to explore based on the process-based reward score. So like in this example, the reward model gives us a low score because it says that 2 + 2 = 5. So you don't explore at all. In this case, it has a higher score, so you allocate more exploration budget to that one, and so on. And then concretely, what it does is you look at your frontier and then you just take the softmax, and that will determine your budget. And of course, this isn't the only tree search algorithm. You can do other ones. And then the question is like, how do you actually get a single answer? Because the tree search can give you multiple outputs. And so the trick here is you can actually just view this as a way of getting candidates for majority voting. So you could basically run the tree search, get n different outputs, and then do best of n or voting. And again, the key difference here with parallel sampling is that it's able to take advantage of these intermediate states. So you could either backtrack or you can alter the compute that you use for exploration. For example, you can kind of decide not to continue the output that has 2 + 2 = 5. So here's showing an evaluation. And on the x-axis, this is actually controlling for the amount of tokens that you're generating. And you can see here that the error, so here lower is better. The error with the tree search procedure is lower than if you use sampling, again, with either majority voting or the best of n. And so it's kind of cool. It's showing that, it is possible to actually design one of these tree search algorithms that does better than the parallel sampling, even when you control for the compute budget, so like the amount of tokens that you're generating. So what are some other areas where tree search has been used? Well, one that doesn't necessarily involve language models. The famous one is Go. Tree search was a really key part of the AlphaGo system and the later models. One kind of in between Go and natural language that does use language models is these formal proofs. These are nice because you can decompose the process into states that you get from the proof assistant. And then you can basically just like generate one step at a time and do a tree search. And basically any state-of-the-art system for these formal proofs does actually use a tree search. And then finally, people have begun exploring doing tree search in different agent environments. Again, the nice thing here is that you can potentially at each step get some new information from the environment. And so potentially if your search algorithm kind of uses that information, then it could be beneficial. This is from a paper from JY and Daniel and Russ here at CMU. So again, the tree search meta generators can backtrack and explore. However, in practice, they do require a environment that's kind of suitable for tree search. And they really do depend on whether you can learn a good value function. So that was tree search. And the last pattern that I'll tell you about is called refinement. So here, again, the idea is very simple. You want to take in some generation that is somehow suboptimal or bad. And you want to pass it to your refinement module or meta generator, and then get a generation that's better. So in practice, to implement this, there's different design choices. So one thing you can do is that you can have your initial generation and then get some form of feedback on the generation. And then you pass both the generation as well as the feedback to a corrector or refinement model. And so the key question, if you do this, is where do you get this feedback from? And how high quality or how noisy is the feedback? So there's kind of two cases. One case is at inference time, you are receiving some external information. And the other case is you're not receiving external information and the whole system is kind of self-contained. So I'll show you what I mean by that with some examples. So here's one case in code generation. So code generation is one area where you can potentially get some form of external feedback. Here, for example, we are trying to generate Rust code. And so initially you get some Rust code and it turns out to be buggy. So now this is kind of an extreme case, but it turns out that for some Rust code, you can actually have this formal verifier. So this formal verifier is called Varus. And the nice thing is that when you call it, it can give you these very detailed error messages. So first of all, it could tell you whether the program passes the specification that you give it or not. And then you can see here that it's like literally underlining part of the code. And so this is some feedback that kind of isn't accessible to the language model just on its own. So you can pass this to a refinement or corrector model. And then in this case, it actually is able to fix the error. And in fact, the error was right where this error message told you it was. So these different cases with code, if you have a verifier or maybe less extreme cases to have a compiler or run some test cases or have an interpreter, those have been some of the success cases of these refinement algorithms. In other cases, you might have a human who's providing feedback. you may have experienced this yourself if you're using like ChatGPT and you kind of point out a specific thing for it to fix, and sometimes it's able to. Or if you have another external system like a retriever, then yeah, these refinement methods have been, pretty promising in these cases. Another case is if you try to have a kind of self-contained refinement system. So here you generate, and now you just re-prompt the same model with a kind of minimal prompt to provide feedback on the output. And then you again re-prompt the model to correct the output. Here, the results, kind of broadly speaking, have been more mixed. And one thing that it comes down to is how easy it is for the evaluator, for the language model to kind of evaluate its own outputs. And so when you think about it, like some tasks are naturally kind of easy to evaluate. Like let's say the task is to generate some paragraph and it has, 10 pieces of information. Then maybe the model generates some like amazing paragraph, but it has 9 out of the 10 pieces of information. Then if the model evaluates it, it's kind of easy to, see that it's incorrect, and then it can refine it into a final output. The one area where it's been a lot more mixed is in these kind of difficult reasoning problems. So there's this paper which is linked to here, and they did this pretty cool analysis. And they showed that the model would just as often go from a correct output to an incorrect output as it would go from an incorrect one to a correct one. And so this is in some sense saying that it's kind of difficult for at least these models that they tested to judge whether their own solutions were correct or not. And as a result, the refinement procedure wasn't working that well. To really drive this idea home, you can do a kind of toy simulation. And I think it's actually kind of insightful. So here we want to output this sequence Taylor Swift. And we're going to use a very simple language model. So it's a unigram model. It'll just generate one character independently of all the other ones. And so it's actually really difficult to generate this output sequence because you essentially have to sample all 11 characters at once, and then they have to happen to be Taylor Swift. So then you can have some feedback, which actually tells you exactly which characters are correct or not. And this is kind of an analogy for that verifier that I was showing you before, where it was actually telling us exactly where in the code it was potentially incorrect. And then your corrector is going to only regenerate the incorrect positions. And you can see here that if you have a perfect feedback, then eventually even this like very naive language model can eventually, stumble upon the correct output. But then what it comes down to is if you introduce some noise into the feedback process, then it performs worse and worse. And eventually it even does worse than, just sampling everything in parallel. So it's some analogy for the things I was telling you about before. Then there's a third case, and this one is maybe even more ambitious. And it's, let's not have any source of feedback, but let's directly learn some model that learns to improve outputs. So this might sound a bit crazy at first, but now we're going to actually train the model. And you can imagine that like maybe if you had many, many examples of this, then yeah, these language models are pretty flexible. Maybe they could actually learn to improve outputs. So there's been a few algorithms developed for doing this, and they usually have the pattern of actually generating with your model and then using some reward function to check whether, an output is worse than another one. And then you train your corrector model to basically generate the improved output. Now, there's a really cool paper. Again, this is from Aviral, who is here at CMU. And they basically found that these can be quite difficult to train. So one like degenerate behavior that they can learn is to just ignore this intermediate output and just get really good at solving the task in one shot. So in some sense, it's not really a corrector model. And then what they found is you can design this kind of careful regularization and reinforcement learning procedure to ultimately get some of this correction behavior. So here's an example where they are either running their like self-correction model or just doing parallel sampling. And you can see in this case, they were able to get their self-corrector to perform a bit better. But kind of zooming back out, you know, enabling the correction behavior for really general settings is still an active area of research. So in summary, the refinement methods, yeah, they can be fairly positive if you have this extrinsic feedback signal. It'll really depend on the task, or maybe more specifically on how difficult it is for the model to evaluate itself, if it's kind of self-contained. And then the idea of training or learning how to self-correct is kind of an active area of research. And so far, it requires some fairly specific training strategies. So in the next part of the talk, I'll talk about some ways for thinking about scaling these meta generation algorithms. So the first one says, you know, I've told you about all these different strategies, and you could actually imagine combining them, right? Like maybe you do parallel sampling and then some refinement, or you do a tree search, and within the tree search, you're doing parallel sampling. So the question is like, how should you actually choose between the meta generation algorithms? And one really important thing is that since we are calling the language models over and over, you can't really just look at the end task performance. You also want to take into account the cost. And so there's different definitions of cost. One is you consider the size of your model and then the number of tokens that you're generating. And then, of course, you have to choose some strategy. So you can formalize this as a problem which is called compute optimal inference, where you have a certain compute budget, and then you want to choose the model size, the number of tokens to generate, and the inference strategy that gives you the best performance or the lowest error. And this is a kind of analogy to, if you've heard of it before, there's a similar notion for pre-training, where you try to either choose, you know, train a smaller model for longer, or train a larger model for a shorter amount of time, given some equal compute budget. And in fact, so then we can ask this analogous question: should we actually generate more with a smaller model, or have a larger model and, you know, generate fewer times? So you can do this experiment over different configurations of model sizes and number of generated tokens. And you get what looks like, you know, one of these scaling frontiers that you see in the case of pre-training. So the way you read these is like, okay, the lower the better in some sense. And at each compute budget on the x-axis, you want to look at what is the model size which has the lowest error. And that's sometimes called the compute optimal frontier. And the interesting thing here is it basically says that, like, for some compute budgets, it's actually better to use a smaller model and, you know, generate more. Like in this example, use the 2 billion parameter model instead of the 12 billion one. In this case, if you want to get the best absolute performance, what the right-hand side is showing you is that you still want to just use the largest model you can, and then, just keep sampling from it. And so this is a kind of, emerging area of research, and there's a few papers on it, but figuring out how to allocate things in your meta generation procedure is a kind of active area. Another question is, out of these different generation algorithms, what's actually the best strategy? And here is showing the curve from before, but now we're actually varying the strategy as well. And so you could see here that there's this sophisticated tree search procedure called Monte Carlo tree search. I don't have time to introduce it, but basically you could see here that if you evaluate it on an equal compute basis, then it actually does fairly poorly because it's a very expensive tree search algorithm. On the other hand, if you use this like rebase tree search, then you are, as we saw before, able to do better than the parallel sampling. So the bigger takeaway is that, for your particular application, even for your particular input, in the future, we might be able to design better algorithms that like better allocate the compute. Okay, so let me just quickly tell you about like two different ways for thinking about how you speed up the meta generators and make them fast. And this section in particular is going to be pretty short, and Haley will give a longer version, and so you could check out the NeurIPS tutorial for that. So again, the meta generators that I told you about are generating a lot of tokens, sometimes in these kind of diverse ways, like tree search. And so how do you do this quickly? Well, one way is to just think about how do you speed up a single generation call? And the second is, if you're generating multiple times, how do you somehow leverage this shared structure that you get? So for speeding up a single generation, there's many different strategies you can use. Just to give you, some flavor, one is you can specifically design your language model architecture for fast inference. Just one example is this grouped query attention, where you switch out the attention mechanism, and one of the motivations for doing it was to get faster inference. Obviously, don't have time to go into the details here. Another is you can compress various parts of the model. So you could compress the weights of the model. You could even compress the activations or the key value cache inside of the transformer. And that can lead to faster inference. And then second or third, you could actually look at the particular hardware that the model's running on, and then do this hardware-aware implementation of the model or the algorithm. So a really famous example of that is flash attention, where they actually look at like the specific way that memory is being managed on the CUDA GPUs, and then you could design like specific kernels to speed up the process. This is a really clever one where you can actually modify the generation algorithm. And so if you remember, I was telling you about these sampling algorithms, like temperature sampling. And in some sense, they're very simple, right? You're just sampling one token at a time. And it's like, how could you possibly speed that up? So there's this clever method called speculative decoding or speculative sampling, where you could actually manage to speed up just the sampling of a single output. And the key idea is you could have a smaller model, which is called a draft model, and it can basically look ahead and propose different tokens. Then you can feed those forward in parallel with your larger model. And so now the larger model is you don't have to call it multiple times. You just do one pass with, say, 4 tokens. And then it could check whether, it could decide whether to accept or reject what the draft model proposed. If you accept them, then you get some speedups. If you reject them, then you actually have to generate with your bigger model. So again, there's actually a whole survey paper about speculative decoding. So another really active area of research, and people have kind of, taken this idea in different directions. And then the final thing you could do is to somehow look at what are the shared structures across your multiple generations. So a really simple example is, let's say you're doing best of n. Well, then the prefix or the prompt that you use is going to be shared over all n calls. And so can you possibly take advantage of that? Well, the most basic thing to do is you can cache the keys and values that are being used in your transformer attention mechanism. Then you could go the next step and look at, okay, how is this key value cache actually being managed at a lower level? And if you've heard of this popular library called VLLM, one of their key innovations was to actually do like better memory management of the key value cache. So they have this idea called paged attention. Now you could try to make it kind of even more fine-grained and say, is there additional shared structure beyond just the prompt? So for example, let's say you have a system prompt, but now for your individual problems, you have different prompts. And then for each one of those problems, you're generating. Or if you're doing a tree search, then, maybe one path you're reusing fairly often. And so these ideas have also been, are being looked into. One popular library, again, you may or may not have heard of it, but it's very useful, called sglang, has this idea of using what is called a radix tree for keeping track of these different prefixes that you encounter. So you can even implement one of these tree searches, and it will kind of cache the different paths of the tree search. And in practice, using one of these libraries can basically just make it possible to even do the tree search. Like without the library, the tree search is like so slow that it's not even practical. So in some sense, like the systems level speedups can actually enable, the development of new meta generators. So again, this is just scratching the surface, and yeah, now we can move to the final part. So again, I told you about the different meta generation strategies. You can think of them as spending test time compute, and then to choose between them, you really should consider both the cost and the performance. Moving forward, I think, you could try composing these and coming up with some hybrid meta generators. So I think that's something we'll see more of. Here's an example where we're combining tree search with refinement. So each kind of transition is itself a refinement. And then there's a variety of really exciting research directions. One that I think a lot of people are thinking about is, how do we actually train models to perform search on their own? This is like the O1 model that I mentioned at the start of the talk. How will things play out in these new agent environments, which are just like now emerging? And then how can we do kind of more fine-grained allocation of the test time compute? And then I should say that like a lot of these conclusions are ultimately based on just a few tasks. So, for the name of science, we should also just explore more tasks and be careful about, how general or how specific the claims or conclusions are. So again, we'll have the NeurIPS tutorial. You could check out the survey paper. And all of the content is really due to, everyone shown here.